Hi, so far we have studied linear motion, that is motion in a straight line, and circular motion, that is something moving around in a circular path. When something moves around in a circular path, it has a fixed center around which it creates a circle or a circular path. In this lecture, we are going to study what we call rotational motion. You can think of rotational motion as a more complete version of circular motion. Why? Because rotational motion involves the motion of objects around a fixed rotational axis. So, for example, let's examine a rotating system. When a wheel rotates around a fixed axis, let's say this marker right here, then we have a rotational motion. It is not circular motion because you can forget the beetle for now, all of the points on this rotating wheel are moving around a fixed axis. Okay, it is not only one single object which is creating a circular path. Also, now let's examine the beetle. If the beetle sits on here and does nothing, it is just sitting there while the wheel rotates, you can model it as a uniform circular motion. You can model the motion of the beetle as a uniform circular motion. Why? Because its motion is creating a circle around a center. So we can describe this motion, describe the beetle's motion by using all of the variables that we have seen for uniform circular motion. However, when the beetle decides to hop from one point to another on this rotating wheel, we have two kinds of motion. One, the rotation of the wheel, and the beetle's motion with respect to the rotating wheel. This is different from circular motion. And in fact, when the beetle hops from one point to another on this rotating wheel, we need to define a new quantity for the beetle or the beetle's motion. We call that quantity angular position and denote it with theta. Theta we have previously used for angles. So you can see that this theta is basically an angle and given the name angular position. Let's look closely at the beetle, the red dots on the circular wheel here. As the circular wheel rotates, the beetle hops from point A to point B. As it does so, it moves a circular path or a borderline of a circle called an arc length, denoted with an S. And as we know that from the distance from the center or the fixed axis to the circumference of this path is the radius of that said circular wheel. From math, we know that we can define arc length as S equals radius times the angle created in between the radii, which then helps us define what angular position is. Angular position is the arc length created as something moved in an arc of a circle from A to B divided by the radius of that circle, the distance from the fixed axis of rotation to the circumference of that arced path. Now, some properties of theta include that theta is a function of time, meaning theta depends on time. So point A could have been at t equals 0, point B could have been at t equals some 2 seconds or something. So we can say that the angular position changed from t equals 1 to t equals 2 seconds, or t equals 0 seconds to t equals 2 seconds, whatever you want to say. And theta is just a measure of an angle, it's just a number, and so has no units. However, it is given a measure. Measure is something like a size given to a variable, and that measure is done in radians, because in physics the measure of a circle is usually in radians, and or revolutions or degrees. One revolution is one kind of measure of this theta, equal to 360 degrees, and that is equal to 2 pi radians. Okay, so if you want to go between these three different measures of angular position, then you have to use these conversion factors. That shows us that revolutions, degrees, and radians are three different measures of the same thing, angular position. Okay, the birth of theta, that is angular position, gives rise to other angular variables. Theta gives rise to angular velocity denoted by omega, or the Greek W. And omega is defined as the angular velocity, since velocity, if we remember from linear motion, was nothing but the change in displacement over time. Omega is another kind of velocity named angular velocity, must be defined as the change in angular displacement delta theta over delta t, the change in time. And the SI unit of this omega is radians per second. Radians is not a unit, as we have just talked about. It's a measure of the angle or the angular position. However, time is measured in the units of seconds. So omega as a whole has units of radians over seconds. Now omega, the angular velocity, gives rise to angular acceleration when omega isn't constant. When omega changes, like when velocity changed in linear motion, we gave rise to an acceleration. When omega changes, when angular velocity changes, we give rise to an angular acceleration. We denote it with alpha, and alpha is defined as the change in omega, or the change in angular velocity over change in time. And the SI unit for alpha is, since omega is in radians per second, we just have a delta t downstairs for alpha. The SI unit for alpha is just radians per second squared. Now it's time to connect the two different types of motion, linear motion and angular motion. How do we do that? Well, let's start off with seeing the corresponding quantities between linear and angular motion. In linear motion, we had delta x, which was nothing but change in displacement. In angular motion, its corresponding variable or quantity is angular displacement, delta theta. In linear motion, we also had delta v, which is the change in velocity, while in angular motion, we now have change in angular velocity, delta omega. And linear motion, a defined acceleration, or a denoted acceleration, while in angular motion, alpha denotes angular acceleration. We also know that we defined 5 sets of kinematic equations for constant acceleration in linear motion. The equations, by far, we know very well, these 5 equations. Since we have similar quantities in angular motion, it is only logical that we have connecting equations for angular motion as well. And we just replace the variables that we had in linear motion with the corresponding variables for angular motion, and everything else stays the same. For example, let's take the first equation, Vf equals Vi plus A times delta t. Vf, the corresponding angular quantity, would be omega f, or omega final, equal to Vi would be replaced by omega I, the initial angular velocity, plus A would be replaced by the angular acceleration, which is constant, and delta t is delta t, because linear motion was a function of time, angular motion is also a function of time, so t remains the same throughout. Okay, so we can take each of these equations and replace them with the correct corresponding variables for angular motion to get our angular motion kinematic equations. And these kinematic equations are valid for constant angular acceleration. Alright, let's look at a few examples now to test our ideas. Okay, so the first problem examines a Blu-ray which rotates from rest to 500 revolutions per minute in 5.5 seconds. So what do we know so far? We have a rotational motion because something is rotating, and a disk rotates around a fixed center axis or fixed axis of rotation from rest. So initially it was at rest to 500 revs per minute, and revs per minute is the unit for radians over time or angle over time, right? Angle over time means we are dealing with the final velocity here, final angular velocity in 5.5 seconds. So the time is also given. What is its angular acceleration? All right. Now, just like we used to do in kinematics long time ago, we will note down all the quantities we know from this problem. We know initially the Blu-ray disc, before it started rotating, it was at rest, meaning rest now means it is both at rest rotationally, and also if there was a linear velocity, it started from rest. So omega I is equal 0 as well as Vi was 0. Okay, and its final speed was given to be 500 revs per minute. Now remember, revs per minute is not SI unit. SI unit is radians per second for omega. So we have to convert this. Keep that in mind. But first let's note down all that we have. The time taken to reach this final speed from 0 radians per second is 5.5 seconds. What do we want to know? We want to know what this acceleration was, and we assume that this acceleration is a constant, because otherwise our angular kinematic equations doesn't work. Now let's get back to first converting this to SI. We know that one revolution is equal to 2 pi radians, and 1 minute is equal to 60 seconds. Okay, minutes to seconds, we are going from a bigger unit to a smaller unit. Revolutions to 2 pi radians, we are going from a bigger unit to a smaller unit. So let's convert this. Omega f given to us as 500 revs per minute. That means the rev needs to go away. So we need to have something revolution down here. So we know that one revolution is 2 pi radians. So this revolution here and 2 pi down here, up here, okay? Then you multiply that by, you have to cancel out minutes, and so we divide by 60 because we are going from bigger to smaller. So minute over 60 seconds. So the minutes can cancel out, the revolutions can cancel out, and this comes out to be omega f is equal to 52.4 radians per second. All right, this is our omega f, but this is not our target. We just converted it to SI units. Now let's think about what equation we can use. We know omega I, we know omega f, we know delta t, we want to find alpha. So we need an equation with all four of these quantities. The first equation works for us. Omega f equal to omega I plus alpha times delta t. Omega f is 52.4 radians per second. Omega I was 0. Alpha is what we are looking for, and the time it took was 5.5 seconds. So alpha is nothing but 52.4 over 5.5. The units were 52.4 had units of radians over second, and time had units of second, and you divide by time, so we have 1 over second. So the unit of alpha is radians per second squared, so it's right, and the result comes out to be 9.5 radians per second squared. All right, now there's a second part to this problem. The second part asks us what is its angular displacement, what is the angular displacement of the Blu-ray disc during this 5.5 second period. So angular displacement is nothing but delta theta, and this is our target, right? And these are the quantities we know so far. We have found alpha to be 9.5 radians per second squared as well. How do we find delta theta? We can now use most of our any of our five equations mostly. Let's go for, since we are finding delta theta, let's keep delta theta separate on one side. Let's go for this equation. Delta theta is equal to omega I delta t plus 1/2 alpha times delta t squared. Delta theta is what we are looking for, so we keep that as such. Initially the disk was at rest, so this whole term goes to 0. What we have left with is 1/2 times alpha, which we found to be 9.5 radians per second squared, times delta t squared, 5.5 second squared. Alright, so the second squares go away and you end up with the measure of theta. Remember, theta didn't have any units, radians is not a unit, so the unit is actually seconds and that goes away. So we end up with angular displacement of 144 radians. Alright, and a side note here, when you're working on rotational motion problems, remember to switch your calculator mode to radians and not degrees. Okay? Now there's a third part to this problem. It asks, during that spin, how far does a point on the rim of the disk with radius 6 centimeters move? Let's first understand what how far means. How far implies the distance moved as the disk rotates about a fixed axis. Distance is a linear quantity, right? And so this is nothing, when rotating, this is nothing but arc length. Okay? And we know that arc length is denoted by S and related to our angular position. S equals radius times the change in angular displacement. Therefore, we can actually calculate what S is, and that is what the question is asking. S is equal to, the radius is 6 centimeters. So let's take 6 to meters by dividing 6 centimeters by 100 times delta theta. Delta theta is the position, the displacement, angular displacement, which we found to be 144 radians. And this comes out to be 8.64 meters. Therefore, we see that S, the arc length, is actually a linear quantity with a linear unit. Okay? What does this tell us? We started off with an angular motion problem or a rotational motion problem, and then we ended up with a linear quantity by using angular position. This shows a connection between linear motion and angular motion. Right? Since there is a linear distance connected to the angular displacement, then there should be a corresponding linear velocity connected to angular velocity. That velocity is known as tangential velocity and defined as V equal to the radius times the angular velocity, omega. Okay, how did we get through to this equation? Well, let's compare this equation to that equation. S, the arc length, the linear quantity, was related via the radius of the rotational circle times the angular position of any of the point on that rotational circle. So this is a direct relation with the constant radius connecting them. And similarly, velocity is nothing but the change in linear position. So if you consider the rate of change of this S, we would have S over T, or the change in S over T would be change in theta over T. Change in theta over T is nothing but omega. So we end up with V equals R omega. Since there is a tangential velocity, naturally there should be a tangential acceleration if this velocity is changing. the tangential acceleration is similarly defined as A equal to AT, let's call it AT, and let's call it just VT for us to not confuse ourselves. AT is equal to, it's also connected via radius because velocity is connected to omega over radius, by radius. So VT, if you change it delta V over time, then we have radius is fixed, it doesn't change, it's a constant for any circle. Then omega, delta omega divided by delta T is nothing but alpha. So we have this relation R alpha. That is my angular acceleration. Let's look at another example to understand these things a little bit better. Alright, this example talks about a car which has 55 centimeter diameter tires coming to a stop over a distance of 14 meters. How many revolutions did each car make while or each tire make while stopping? What are the information given to us? The car has 55 centimeter diameter tires. So the tires that are rotating has diameters of 55 centimeters, and the car comes to a stop over a distance of 14 meters. So it comes to rest after it has covered a distance of 14 meters. Alright, how does it cover a distance of 14 meters? The tires rotate, the total rotating distance is 14 meters. How many revolutions did each tire make while stopping? Revolutions is our target. Let's think about it. So we have a tire. Each tire has this property. It has a diameter of 55 centimeters and it rotates and rotates to a stop covering a rotating distance of 14 meters. Rotating distance is nothing but the arc length, and the rotating this distance that the tires come to a stop at is related to the angular position of any point on this circular tire, and we know that S equals R theta. What is the radius? Radius is nothing but half of the diameter. So radius is 55 over 2 meters or centimeters. Now centimeters is not SI unit, so we have to divide that by 100 to get this quantity in meters, right? So the target is revolutions. Revolutions is a measure of angular position. Okay, so this theta is our target. Then theta is equal to S over R. S over R. What is S? S is 14 meters. And what is R? R is, whatever this comes out to be, 55 over 2 over 100 meters. So the meters go away. And we have theta equal to, when you have meters over meters, your original measure of theta for physics problems like these should always be in radians. Okay, so this comes out to be 50.9 radians. Okay, however, we want revolutions, which is a different measure from radian. So what do we know about that? We know that one revolution is equal to 2 pi radians. So if you want to go from radians to revolution, we have to do this. Theta should be equal to 50.9 radians multiplied by 2 pi radians down here and 1 revolution up here. So we are basically dividing radians by 2 pi because revolutions is a bigger measure than radians. So we divide to get rid of this radians, and this comes out to be around 8.1 revolutions. So it takes the tires 8.1 revolutions around the fixed axis of rotation to come to a stop with a distance of 14 meters. I hope this topic of rotational motion makes sense.